Hello friends, welcome back to my channel and the UPSC Mains Geography series. If you watched our Indian monsoon video, which was part 1 of this series, you already know how El Nino weakens the monsoon, how the Indian Ocean Dipole saved India's 2019 monsoon despite El Nino, and how the Madden-Julian oscillation drives active and break spells within the monsoon season. If you have not watched that video yet, I strongly recommend you pause right now, watch the Indian monsoon video first and then come back here. The link is in the description below because this session is part 2 and it builds directly on what we covered there. In this session, ocean currents and ENSO, we go deeper. We answered the questions that the monsoon video raised but did not fully explain. What are ocean currents and why do they flow the way they do? What is the Walker circulation, the atmospheric engine that connects the Pacific Ocean to India's rainfall? What exactly is El Nino and La Nina and how do they form? What is the Indian Ocean Dipole, the Madden-Julian oscillation and the Pacific Decadal oscillation? And how does climate change alter all of these? Notice the 4 statistics at the bottom of the screen. The ocean covers 360 million square kilometers, 71% of Earth's surface. The deepest point, the Mariana Trench, plunges to 11,034 meters. The average temperature below 1,000 meters is just 4 degrees Celsius, near freezing. And there are over 30 major ocean currents mapped globally. The ocean is not just water, it is the climate engine of our planet, and mastering it is essential for UPSC GS1. Let us begin. Here is our roadmap for today. 10 modules, each one a self-contained deep dive that you can also use for revision before the exam. Let me give you a 30-second overview so you know where we are headed. Modules 1 to 4 build the foundation. We start with how oceans circulate, the Thermohaline conveyor belt, Coriolis force, and the two-layer system. Then we map all the major warm and cold ocean currents. Then we understand how those currents shape climate, temperature, rainfall, fog, fisheries. And then we take a special India-focused look at Indian ocean currents and their unique seasonal reversal. Modules 5 to 8 are the heart of this session. The ENSO and Teleconnections system, Walker circulation, El Nino, La Nina, the Indian Ocean Dipole, the Madden-Julian oscillation, and how all of these factors interact to determine India's monsoon outcome in any given year. Module 9 brings in climate change, how ocean warming, AMOC slowdown, and marine heat waves are altering all these systems. And Module 10 gives you the complete UPSC toolkit, previous year questions, data facts, and the answer writing framework. Let us start with Module 1. Module 1, Ocean Circulation Basics. Before we talk about specific currents, we need to understand the two-layer system of ocean circulation and the 5 forces that drive it. This is the foundation that makes everything else make sense. Think of the ocean as having 2 completely different circulation systems stacked on top of each other, like 2 different weather systems in the same sky. The top layer is the surface circulation, roughly the top 200 meters of the ocean. This layer is warm, less dense, and is driven almost entirely by wind. The trade winds and westerlies drag the surface water along with them, creating the major surface currents we will study shortly. This layer absorbs sunlight. Temperature ranges from 15 to 30 degrees Celsius depending on latitude. Below this is the thermocline, a transition zone between 200 and 1000 meters depth where temperature drops sharply. This thermocline acts as a barrier. It inhibits mixing between the warm surface water above and the cold deep water below. The existence of this barrier is crucial for understanding El Nino. When El Nino develops, the thermocline deepens in the East Pacific, which is one of its defining features. Below 1000 meters is the deep ocean, and here the driving force is completely different. Wind cannot reach this deep. Instead, the deep ocean is driven by density differences, specifically by differences in both temperature and salinity. This is why it is called thermohaline circulation. Thermo means temperature, haline means salt. Here is how it works. In polar regions like the North Atlantic near Greenland and around Antarctica, the surface water becomes very cold and very salty. As ice forms, ice is fresh water. When it freezes, it leaves salt behind in the surrounding water. Cold water is denser than warm water. Salty water is denser than fresh water. So, this extremely cold, extremely salty polar water sinks. It becomes heavier and drops to the ocean floor. This sinking polar water then flows along the ocean floor as a deep cold current, pushing warm water at the surface to flow toward the poles to replace it. This creates a global conveyor belt, also called the Atlantic Meridional Overturning Circulation, or AMOC, that moves water continuously around all the world's oceans over a period of roughly 1000 years. Now look at the 5 driving forces on the right side of the screen. Wind is the primary driver of surface currents. The trade winds blow from east to west near the equator. The westerlies blow from west to east in mid-latitudes. These create the major surface current patterns. Temperature differences create density gradients that drive the thermohaline circulation. Salinity gradients also affect density. The Mediterranean Sea, for example, is so evaporation heavy that it produces dense, salty water that overflows into the Atlantic at depth. The Coriolis force, Earth's rotation, deflects moving objects to the right in the northern hemisphere and to the left in the southern hemisphere. This deflection is what causes ocean currents to form circular loops called gyres, clockwise in the northern hemisphere, anti-clockwise in the southern hemisphere. And finally, sea floor topography. Submarine ridges, trenches, and basins channel and redirect deep water currents. The Mid-Atlantic Ridge, for example, divides the deep Atlantic into eastern and western basins with different circulation patterns. UPSC connect. The Coriolis force creating gyres, the thermohaline conveyor belt, and the thermohaline circulation are all examined directly in UPSC 1. Remember, surface circulation is wind driven, deep circulation is density driven. Module 2, Major Ocean Currents. Now that we understand the forces that drive ocean currents, let us map the specific currents. Warm first, then cold, covering the Atlantic, Pacific and Indian Oceans. I want you to visualize each current's route as we go through them. Warm ocean currents. They carry warm equatorial water toward the poles. Warming the coasts they flow past and bringing moisture and rainfall. The Gulf Stream is the most famous ocean current in the world. It originates in the Gulf of Mexico, flows northeastward along the eastern coast of the United States, and then swings across the Atlantic toward Europe. Its speed, 2.5 meters per second, makes it the fastest ocean current, with 80 kilometers. It carries as much water as 50 Amazon rivers combined. The Gulf Stream is the reason that Western Europe, especially Britain, Ireland and Norway, has a climate far warmer than its latitude would suggest. London is at the same latitude as Calgary, Canada, yet London's winters are mild while Calgary's are brutal. That difference is largely the Gulf Stream. It merges into the North Atlantic Current, also called the North Atlantic Drift, as it extends toward Europe. The Kuroshio current is the Pacific equivalent of the Gulf Stream. Kuroshio means black current in Japanese, named for its deep blue, extremely clear water. It flows northeastward along Japan's Pacific coast, warming Japan's climate. It merges into the North Pacific Current, which carries warm water toward the North American coast. The North Equatorial Currents, both Atlantic and Pacific have them, flow westward, driven by the trade winds. These are the source currents that feed into the Gulf Stream, Atlantic and Kuroshio, Pacific. Understanding this is important for ENSO. During El Nino, when the trade winds weaken, this westward flow slows down and warm water stays in the central/eastern Pacific instead of piling up in the west. The Brazilian current flows southwest along Brazil's coast, part of the South Atlantic gyre. It eventually meets the cold Falkland Current, also called Malvinas Current, near 40 degrees south latitude. This confluence zone is one of the world's richest fishing grounds. The Agulhas Current flows southwest along South Africa's east coast. It is the fastest western boundary current in the southern hemisphere. At its southern end, near the Cape of Good Hope, it does something spectacular. It retroflects, turning sharply back eastward. In doing so, it sheds large warm water eddies into the South Atlantic. These Agulhas leakage eddies are important for Atlantic circulation and are becoming larger due to climate change. And the North Atlantic Drift, the extension of the Gulf Stream into the subarctic, keeps Norway's fjords and the Russian port of Murmansk ice-free year-round despite being at 70 degrees north latitude. This has been strategically important for centuries and climatologically important as a signal of thermohaline circulation strength. For UPSC, remember the general rule: warm currents flow along the eastern coasts of continents in the northern hemisphere. Gulf Stream on US east coast, Kuroshio on Japan's east coast, and along the western coast of continents in the southern hemisphere. Brazilian current on Brazil's coast, Agulhas on South Africa's east coast. Now, cold ocean currents. These flow from polar regions toward the equator, chilling the coast they pass and often creating aridity and fog. The Labrador current flows southward from the Arctic along Canada's east coast. It is cold, dense, and carries icebergs as far south as Newfoundland. When it meets the warm Gulf Stream at the Grand Banks, one of the most dramatic oceanic collisions on Earth, the result is two things: extraordinary fishing, because nutrients from both currents mix in a shallow productive zone, and dense fog because warm, moist Gulf Stream air moves over the cold Labrador current surface and condenses. The Grand Banks of Newfoundland is one of the world's densest fog zones, and this fog was directly responsible for the Titanic disaster in 1912. The Canary Current flows southwestward along northwest Africa, Portugal, Morocco, and the Canary Islands. As a cold eastern boundary current, it suppresses evaporation from the ocean surface, keeping the overlying air dry. This is the primary reason the western edge of the Sahara Desert reaches all the way to the Moroccan coast. The Canary Current also drives powerful upwelling of cold, nutrient-rich deep water, creating extraordinarily rich fisheries along Morocco, Mauritania, and Senegal. The California Current flows southeast along the US Pacific coast, California, Oregon, Washington. Same mechanism as the Canary Current, cold eastern boundary current, creates the characteristic cool foggy climate of San Francisco despite it being at a relatively warm latitude. Also drives upwelling that supports California's rich fisheries. The Peru Current, also called the Humboldt Current, is one of the most important ocean currents on Earth from a human perspective. It flows northward along South America's Pacific coast, Chile, Peru, Ecuador. The upwelling it drives makes the coastal waters of Peru one of the richest fishing zones in the world. Historically, Peru was the world's largest fishing nation by volume, primarily harvesting anchoveta anchovies. The cold current also makes the adjacent coastal desert, the Atacama, one of the driest places on Earth despite being a coastline. And critically, during El Nino, this cold current weakens or disappears. Warm water replaces it, upwelling collapses, fish populations crash, and the Atacama gets catastrophic floods. This is why El Nino is so economically devastating for Peru. The Benguela current flows northward along southern Africa, Namibia, Angola. Like the Canary and California currents, it is a cold eastern boundary current with intense upwelling. The Benguela current makes Namibia's coast one of the richest fishing zones in the world and keeps the adjacent Namib Desert, literally a coastal desert, extremely arid, and the Antarctic Circumpolar Current, the largest ocean current on Earth. It flows continuously eastward around Antarctica, completely unobstructed by any land mass, going around and around the Southern Ocean indefinitely. It connects all three major ocean basins and is the primary driver of global thermohaline circulation. Climate change disrupting this current would have catastrophic global consequences. UPSC key cold currents flow along western coasts of continents in both hemispheres: Canary, West Africa; California, West USA; Benguela, West Southern Africa; Peru, West South America. This is why west coasts of continents at tropical latitudes tend to be A or D. Classic exam question. Module 3: How ocean currents shape climate, fisheries, and human geography. We have named the currents. Now let us understand their effects on temperature, rainfall, fog, fisheries, and storm tracks. Each of these effects is directly UPSC examinable. 6 critical effects of ocean currents. Let us go through each one as a clear cause and effect relationship. Effect 1: Temperature moderation. Warm currents raise temperatures of the coasts they flow past by as much as 10 degrees Celsius compared to the same latitude inland or on the opposite coast. The North Atlantic drift keeps Britain and Norway dramatically warmer than the same latitudes in Canada. Cold currents lower temperatures. The Benguela current keeps Namibia's coast 10 degrees cooler than it would otherwise be. The UPSC exam regularly asks, why does Western Europe have a milder climate than Eastern Canada at the same latitude? The answer is the warm North Atlantic drift. Effect 2: Rainfall and aridity. Warm currents increase evaporation over the ocean surface. The air above becomes moist, and when this moist air moves on shore, it brings rainfall. This is why the windward coast of continents that receive warm current winds get heavy rainfall. Cold currents do the opposite. They cool the air above them, reducing its capacity to hold moisture. The air above a cold current is stable. It does not rise and form clouds. Winds blowing off a cold current onto land bring dry weather. This is why the Sahara, Atacama, Namib, and the dry areas of the Baja California coast all occur at the same longitude as cold ocean currents. Effect 3: Fog formation. When warm moist air moves horizontally over a cold current surface, the air is chilled from below and its moisture condenses into tiny droplets, creating advection fog. This is different from radiation fog, which forms at night over land. The Grand Banks fog zone of Newfoundland, where the warm Gulf Stream meets the cold Labrador current, is the world's densest persistent sea fog. San Francisco's famous fogs come from the cold California current. Seafarers have navigated these fog zones for centuries with significant danger. Effect 4: Fisheries and upwelling. This is critically important. When a cold current creates upwelling, where deep, cold, nutrient-rich water is pulled to the surface, it creates extraordinary marine productivity. The nutrients feed phytoplankton, which feeds zooplankton, which feeds small fish like anchovies, and sardines, which feed larger fish and marine mammals. The world's major fishing grounds are all at cold current upwelling zones: Grand Banks, Labrador plus Gulf Stream, Peru coast, Humboldt, Benguela, Southwest Africa, Canary, Northwest Africa. Peru's upwelling zone was producing 20% of the world's entire fish catch before El Nino disruptions. Pause. Effect 5: Hurricane and cyclone tracks. Ocean currents determine where tropical cyclones intensify and where they die. Tropical cyclones need sea surface temperatures above 26 to 27 degrees Celsius to form and maintain themselves. Warm currents provide this energy. The Gulf Stream fuels Atlantic hurricanes. The Kuroshio fuels Pacific typhoons. Cold currents prevent cyclone formation, which is why the US Pacific coast, despite being tropical at its southern end, almost never gets hurricanes. The cold California current keeps those waters too cool for cyclone development. Effect 6: The El Nino disruption effect. This is the most important for UPSC. When El Nino develops, it disrupts the normal pattern of ocean currents, particularly in the Pacific. The Peru/Humboldt cold current weakens or reverses. The upwelling collapses, fish populations crash, the normally arid Peru coast floods, and the disruption propagates globally through atmospheric teleconnections, weakening the Indian monsoon, causing drought in Australia, and altering weather patterns as far away as Africa and North America. Every one of these 6 effects has appeared in UPSC papers. Know them with examples. Module 4. Indian Ocean Currents. The Indian Ocean is unlike any other ocean on Earth. Its currents do not follow a fixed pattern year-round. They reverse completely between summer and winter. This makes the Indian Ocean uniquely important for understanding the Indian monsoon. The Indian Ocean has a remarkable feature that no other ocean has. Its surface currents completely reverse direction twice a year, driven by the seasonal reversal of the monsoon winds. In the Atlantic and Pacific, currents flow in the same direction year-round. In the Indian Ocean, especially the northern part, the currents in June look almost exactly opposite to the currents in January. During summer, June to September, the southwest monsoon winds blow from the southwest toward the northeast. These winds push the surface water northeastward. This is the southwest monsoon drift. The entire northern Indian Ocean surface moves in this direction, and the Somali current, which flows along the coast of Somalia and East Africa, reverses to flow northward at extraordinary speed. The Somali current during summer is the world's fastest ocean current at 3.5 meters per second, and this fast northward flow generates powerful upwelling off the coasts of Somalia and Oman, creating very high marine productivity in the Arabian Sea during summer. During winter, November to February, the northeast monsoon winds reverse, blowing from the northeast toward the southwest. The surface currents reverse accordingly to form the northeast monsoon drift flowing southwestward. The Somali current reverses to flow southward. The north equatorial current is re-established. This seasonal reversal has practical importance for India. During the Arab trading era, Dachau sailors used these predictable current reversals to time their voyages northeast to East Africa in winter with the NE monsoon, back to Arabia in summer with the SW monsoon. The Indian Ocean was the world's first monsoon commerce system. The Agulhas current on South Africa's east coast continues year-round southwestward. Its retroflexion, where it turns sharply back east, is becoming more pronounced due to warming southern ocean temperatures, and Agulhas eddies penetrating into the Atlantic are affecting global circulation. The West Australian current flows northward along Australia's west coast as a cold eastern boundary current, keeping Western Australia's coast cooler and creating arid coastal conditions similar to the Benguela in Africa. UPSC Gold Fact: the seasonal reversal of Indian Ocean currents is directly caused by the monsoon. The same differential heating of land and sea that drives the monsoon winds also reverses the ocean currents. Monsoon and ocean currents are two faces of the same system. Key concept: Indian Ocean equals only ocean with seasonal current reversal. Somali current equals world's fastest at 3.5 meters per second in summer. This reversal is driven by the same differential heating that drives the monsoon. Module 5. Walker Circulation and ENSO. We are now entering the core of this session, the engine that drives global climate variability. The Walker Circulation is a giant atmospheric loop in the tropical Pacific, and when it changes, the entire global climate system shifts. El Nino is what happens when this engine stutters. Let us understand it completely. The Walker Circulation is named after Sir Gilbert Walker, a British meteorologist who discovered it in the 1920s while trying to predict Indian monsoon failures. So its connection to India's rainfall is built into its very history. Look at the diagram on screen. Let me walk you through the normal state first. In the normal state, the Western Pacific, near Indonesia, Papua New Guinea, and Northern Australia is very warm. Sea surface temperatures here reach 29 to 30 degrees Celsius. Warm water heats the air above it, causing the air to rise rapidly. Rising air cools, condenses, and creates heavy rainfall. Indonesia and northern Australia get drenched. In the eastern Pacific, near Peru and Ecuador, the cold Humboldt current keeps the ocean surface cool, around 22 to 24 degrees Celsius. Over this cool water, the air is stable and sinks. Sinking air is dry air. It does not form clouds or rain. Peru's coast is desert. Now, at the surface level, the air flows from east to west across the Pacific, driven by the southeast trade winds. This surface flow pushes warm water westward, piling it up in the western Pacific and deepening the thermocline there. The East Pacific has shallow thermocline and cold upwelling. In the upper troposphere, the air that rose over the West Pacific flows back eastward, completing the loop. This full loop, rising in west, flowing east aloft, descending in east, flowing west at surface, is the Walker circulation cell. Now, how does this connect to India's monsoon? The same Walker circulation drives moisture-laden southeast trade winds across the equator. These cross the equator, are deflected by the Coriolis force, and become the southwest monsoon winds that bring rainfall to India. A strong Walker circulation equals strong trade winds equals strong moisture transport equals good monsoon for India. Now look at the three states at the bottom of the screen. Normal state, Walker circulation fully developed. Trade winds push warm water west. Cold Humboldt upwells in East Pacific. India gets a normal to good monsoon. El Nino state, Walker circulation weakens. Trade winds slacken, sometimes even reversing. Warm water that was piled up in the West Pacific sloshes back eastward. The Eastern Pacific warms dramatically. Upwelling in Peru collapses. The rising air zone shifts toward the Central Pacific. Rainfall redistributes. Peru floods. Australia droughts. India's monsoon weakens. El Nino state, Walker circulation strengthens, becomes even more intense than normal. Trade winds increase. Eastern Pacific becomes extra cold. Rising air zone shifts further west than normal. India gets above normal monsoon. Australia gets floods. UPSC one-line summary. Strong Walker circulation equals La Nina equals good India monsoon. Weak Walker circulation equals El Nino equals poor India monsoon. El Nino and La Nina together form the ENSO cycle, the El Nino Southern Oscillation. Let me teach you each one in detail. El Nino, the warm event. The word El Nino is Spanish for the child, specifically the Christ child, because Peruvian fishermen named it for the warm ocean anomaly that appeared around Christmas time, ruining their fishing. Definition: El Nino is an anomalous warming of the central and eastern Pacific Ocean by more than 0.5 degrees Celsius, maintained for 5 or more consecutive months, measured in a region called 90 3.4 between 5 degrees north and 5 degrees south latitude. Mechanism: it begins when the southeast trade winds weaken, sometimes due to random atmospheric variability, sometimes due to other climate signals. When trade winds weaken, they can no longer hold back the warm water in the West Pacific. The warm water sloshes eastward along the equator. This is called a Kelvin wave. The thermocline in the East Pacific deepens, suppressing the cold upwelling. Sea surface temperatures in the central/eastern Pacific rise dramatically. India impact: the warm eastern Pacific disrupts the Walker circulation. The rising air zone that was over Indonesia now shifts toward the Central Pacific, taking rainfall with it. The descending branch of the Walker circulation intensifies over India. Descending air equals subsidence equals dry conditions. India's monsoon is suppressed. The Indian Meteorological Department treats the ENSO index as its primary predictor in the April long-range forecast. Historical droughts: look at this list. 1877, the Great Famine, deadliest drought in Indian history. Millions died. 1918, 1987, 2002, 2009, 2015. All of these deficit or drought monsoons coincided with El Nino events. The correlation is strong but not deterministic. Not every El Nino causes drought because the Indian Ocean dipole and other factors can counteract it. Global impacts: El Nino causes Australia and Indonesia to dry out. Peru and Ecuador experience catastrophic floods. The Atlantic hurricane season is suppressed because El Nino creates upper level wind shear that tears apart hurricanes. East Africa gets surplus rainfall. It is truly a global reshuffling of rainfall patterns. El Nina, the cool event. La Nina is the opposite, an anomalous cooling of the central eastern Pacific. The same mechanisms but in reverse. Trade winds intensify, pushing more warm water into the West Pacific. Cold upwelling in the East Pacific strengthens. The Walker circulation becomes more powerful. India impact enhanced Walker circulation sends stronger moisture flow toward India. Active monsoon spells become more frequent and intense. India typically receives 10 to 15% above the long period average in strong La Nina years. Historical floods 1988, 1994, 2010. The 2010 Pakistan mega floods, which killed 2,000 people and displaced 20 million, were during a strong La Nina. 2020, 2022, all strong La Nina years. Important nuance. La Nina is generally good for India's monsoon, but not always good overall. It can trigger devastating floods in vulnerable areas. More rainfall does not always mean better outcomes if infrastructure cannot handle it. Module 6. The Indian Ocean Dipole. If El Nino is the villain in India's monsoon story, the Indian Ocean Dipole is sometimes the unexpected hero, the force that can completely counteract El Nino's suppressing influence. And the most dramatic example of this, the 2019 paradox, is one of the most important case studies for UPSC. The Indian Ocean Dipole, or IOD, is to the Indian Ocean what ENSO is to the Pacific. It is a gradient of sea surface temperatures within the Indian Ocean itself. Read the definition carefully. The IOD measures the difference in sea surface temperatures between the Western Indian Ocean, specifically the Arabian Sea, and the Eastern Indian Ocean, specifically the waters near Indonesia and the Eastern Indian Ocean coast. When the West is warmer than the East, that is a positive IOD. When the East is warmer than the West, that is a negative IOD. It was discovered independently by multiple research groups in 1999, relatively recently compared to ENSO, which has been known for over a century, and crucially, the IOD operates independently of ENSO, though the two often interact. Positive EOD, Western Indian Ocean warmer, Eastern Indian Ocean cooler. The warm Arabian Sea sends enhanced moisture directly into the southwest monsoon circulation because the Arabian Sea is the main moisture source for India's western monsoon branch. More moisture from a warmer Arabian Sea equals stronger, wetter monsoon. Positive IOD counteracts El Nino. Negative IOD, Western Indian Ocean cooler, Eastern Indian Ocean warmer. The cooler Arabian Sea provides less moisture to the monsoon. The monsoon weakens. Negative IOD can amplify the damage of an El Nino year, making a bad monsoon even worse. Now, the 2019 paradox. This is the most important real-world case study in this entire module. Read it carefully. In 2019, there was a moderate El Nino in the Pacific, which by historical pattern would tend to suppress India's monsoon. Conventional forecasts would say deficit monsoon likely, but simultaneously there was a very strong positive EOD, the strongest in 50 years, with an index value of plus 2.0. The warm Western Indian Ocean was pumping enormous moisture into the monsoon circulation. The two effects cancelled each other out. India received 110% of the long period average, above normal monsoon despite the presence of El Nino. What does this teach us? It teaches us that the Indian monsoon is not determined by any single factor. It is determined by the combined weighted effect of multiple climate signals, ENSO, IOD, MJO, snow cover, and others. A strong enough positive IOD can completely neutralize a moderate El Nino. This is why monsoon prediction is so difficult. and why IMD's forecasting models have become increasingly sophisticated. Since 2019, the IMD now includes the IOD index as a mandatory predictor in its April long range forecast alongside the ENSO index. Previously, only ENSO was used as the primary predictor. The 2019 episode was a turning point in operational monsoon forecasting. UPSC answer: whenever a question asks, why doesn't every El Nino cause drought? The answer is the IOD. The 2019 case is your example. Key concept: 2019 moderate El Nino, bad for monsoon, plus strong plus IOD, good for monsoon, equals above normal rainfall at 110% LPA. This is the definitive example of multi-factor monsoon determination. Module 7. The Madden-Julian Oscillation or MJO. ENSO and IOD operate on interannual timescales, year to year, but even within a single monsoon season, rainfall is not uniform. Some weeks India drowns in monsoon rains, other weeks it is hot and dry. What drives this within season variability? The answer is the MJO. The Madden-Julian Oscillation, named after meteorologists Roland Madden and Paul Julian, who discovered it in 1971 while analyzing radio sonde data from Canton Island, is an intra-seasonal phenomenon. What does intra-seasonal mean? It means it operates within a season, not between years like ENSO, but week by week within the monsoon season itself. Its cycle length is 30 to 60 days. How it works? The MJO is a large-scale envelope of enhanced convection, cloudiness, rainfall, rising air that propagates eastward around the equator. It is not a fixed region of rainfall but a traveling system. As it moves eastward, it alternates between an active phase, convection-enhanced heavy rainfall, and a suppressed phase, convection-reduced dry conditions. The MJO is divided into 8 phases based on longitude. Phases 2 and 3 over the Indian Ocean, active India monsoon. When the MJO active phase is over the Indian Ocean, it dramatically enhances convection over India and surrounding areas. This corresponds to active monsoon spells, weeks of widespread heavy rainfall across the country. Phases 6, 7, 8 over the Pacific, suppressed India monsoon. When the MJO active phase has moved into the Pacific, the Indian Ocean enters the suppressed phase. India experiences break monsoon conditions, hot, dry, clear skies. This is when the monsoon takes a break. Phases 4 and 5, transitional phases. Phase 1 over Africa, weak signal for India. Practical importance: the MJO cycle of 30 to 60 days means that within a single June to September monsoon season, India typically goes through 2 to 3 active break cycles. This explains why a farmer in central India might experience 2 weeks of flooding, followed by 10 days of dry heat, followed by another active spell. Forecasting revolution: IMD's extended range forecast, which covers day 16 to day 22, now relies heavily on MJO phase analysis. By knowing which phase the MJO is in and where it is heading, forecasters can predict active versus break conditions 2 to 3 weeks in advance. This has transformed agricultural advisories. Farmers can now plan irrigation, harvesting, and planting based on MJO-based extended forecasts. MJO and ENSO interaction. During El Nino, the MJO amplitude over the Indian Ocean is generally reduced. El Nino and MJO suppressed phase compound each other, creating a particularly bad monsoon period. During La Nina, MJO active phases over the Indian Ocean are more organized and intense, amplifying the already enhanced La Nina monsoon. UPSC. Explain intra-seasonal variability of the Indian monsoon equals MJO is the key answer. Specifically mention the 8 phases, the 30 to 60 day cycle, and the extended range forecast application. Module 8. Teleconnections and the Indian monsoon. We have now studied ENSO, IOD, and MJO individually. But the real world is messier than that. All these signals operate simultaneously, sometimes reinforcing each other, sometimes cancelling each other. This module shows you how to think about the monsoon as a multi-factor system, which is exactly what UPSC examiners want to see. A teleconnection is a climate linkage between geographically distant regions, where a change in one part of the world has a predictable effect on weather thousands of kilometers away. The Indian monsoon is the world's best example of a climate system driven by teleconnections. Look at the 6 factors on screen. Let me explain each one and its specific link to India's monsoon. Factor 1, ENSO, the dominant interannual driver. El Niño reduces Indian monsoon rainfall by 15 to 20% on average. La Niña increases it by 10 to 15%. The mechanism, Walker circulation strength, modulates moisture transport to India. Factor 2, Indian Ocean Dipole, the direct moisture source controller. The Arabian Sea is the primary moisture source for India's western monsoon branch. When the IOD is positive and the Arabian Sea is warmer than normal, it directly increases evaporation and moisture availability. Unlike ENSO, which acts through atmospheric circulation changes, the IOD acts as a direct moisture supply change. Factor 3, MJO, the intraseasonal modulator. Not a year-to-year effect, but a week-to-week effect. In any given year, the timing of MJO phases during June to September determines the distribution of rainfall within the monsoon season, whether good monsoon years have concentrated or well-distributed rainfall. Factor 4, Eurasian snow cover. This is a classic UPSC predictive relationship. When winter snow cover over Siberia, Central Asia, and the Himalayas is above normal, the land heats up more slowly in spring because snow reflects sunlight and keeps the ground cold. This delays the development of the thermal low over northwest India that triggers the monsoon. The result, delayed monsoon onset and sometimes a weaker monsoon. IMD includes Eurasian snow cover as one of its long-range forecast predictors. Factor 5, Atlantic Multi-Decadal Oscillation, AMO. The AMO is a cycle of Atlantic Ocean temperatures operating over 60 to 80 year timescales. Half the cycle, the Atlantic is warmer than average, warm phase, half cooler, cold phase. Research shows that warm AMO phases are associated with stronger Indian monsoons on decadal timescales. The mechanism involves changes in the Atlantic meridional overturning circulation affecting global atmospheric circulation patterns. This is important for understanding the multi-decadal variation in monsoon strength, why some decades have consistently stronger monsoons than others. Factor 6, Pacific Decadal Oscillation, PDO. The PDO is the Pacific equivalent of the AMO, a 20 to 30 year cycle of North Pacific temperature anomalies. During the warm PDO phase 1977 to 1998, El Niño events were stronger and more frequent. During the cold PDO phase 1999 to present approximately, El Niño events are less frequent and sometimes weaker. The PDO essentially modulates the ENSO system. It is the background state that controls how strong individual El Niño events are. The UPSC insight, when you write about monsoon variability, do not say El Niño causes drought. Say El Niño is the dominant factor suppressing monsoon, but the outcome in any year depends on the combined and sometimes counteracting effect of ENSO, IOD, MJO, and longer cycle oscillations like AMO and PDO. That nuanced answer shows UPSC examiners that you understand the system, not just one component of it. Key concept: monsoon prediction requires ENSO dominant plus IOD counterweight plus MJO intraseasonal plus snow cover onset timing plus AMO/PDO background state. No single factor alone determines outcome. Module 9, Climate Change and the Oceans. Everything we have studied so far, currents, ENSO, IOD, thermohaline circulation, is being altered by climate change. This module brings in the IPCC AR6 evidence and shows why the UPSC examiner who asks about ocean currents in 2026 will expect you to discuss climate change dimensions as well. Module 10, UPSC Writing Strategy. We have built comprehensive knowledge across 9 modules. Now let us sharpen the ability to use this knowledge in the exam hall. Previous year questions, data facts, and the complete 6-step answer framework. Everything you need to write a top scoring mains answer on this topic. Let us go through the UPSC toolkit for this topic section by section. Previous year questions, 2024. Discuss the role of ocean currents in regulating climate and weather patterns of coastal regions. This is a broad question. Answer structure. Define currents briefly, cover warm versus cool currents and their effects. Use 6 to 8 specific examples with locations. Bring in ENSO as the most dramatic example of current climate interaction. Conclude with climate change. 2022. How does ENSO affect the monsoon in India? More focused. Cover water circulation, El Nino mechanism, La Niña mechanism, historical droughts and floods, and critically mention that IOD can counteract ENSO. 2021. What is the Indian Ocean Dipole? Explain its relationship with Indian monsoon. Define IOD plus IOD slash minus IOD. Explain mechanism. Give the 2019 case study. Explain how IOD modulates ENSO impact on India. 2017. Explain the role of ocean currents in the distribution of rainfall in India. Focus on warm currents bringing moisture to India's coasts, cold currents creating aridity, and ENSO slash IOD controlling interannual variation. High value data facts. Memorize these. Gulf Stream speed 2.5 meters per second. Somali current summer speed 3.5 meters per second. Fastest current in the Indian Ocean. 2019 India monsoon. 110% of LPA despite El Nino due to strong positive IOD. Antarctic circumpolar, largest ocean current on Earth. Mariana Trench 11,034 meters. A MOC is at its weakest in 1000 years. Per IPCC AR6, Indian Ocean is the only ocean with complete seasonal current reversal. Oceans have absorbed 91% of global warming excess heat. El Nino frequency every 2 to 7 years. MJO cycle 30 to 60 days, 8 phases. 6-step answer. Framework. Step 1. Introduction. Do not start with ocean currents or movements of water. Instead, open with the climate significance. The ocean, covering 71% of Earth's surface, functions as the planet's primary climate regulator, redistributing heat through a complex network of currents that determine temperature, rainfall, and extreme weather patterns across every continent. Step 2. Mechanism. Water circulation, Coriolis force, Thermohaline circulation. Explain the drivers. Step 3. Types and classification. Warm versus cold currents, their locations. Warm on eastern coast / cold on western coasts. Step 4. India, focus. Indian Ocean seasonal reversal. Somali current, ENSO and IOD impact on monsoon. The 2019 paradox. Step 5. Contemporary AMOC slowdown, marine heat waves, intensifying cyclones, ocean warming, and acidification. Step 6. Conclusion. Link to INCOAS early warning, blue economy, SDG 14, life below water, SDG 13, climate action, and India's vulnerability to ocean climate disruption. One final thought. In an exam, when you write about climate and ENSO, always show both sides. El Nino equals bad for India, La Nina equals generally good but can cause floods. Never be absolute. Nuance is what separates 8 out of 10 answers from 6 out of 10 answers. Look at the concept map on screen. Ocean currents and ENSO at the center. 8 dimensions radiating outward. Thermohaline circulation, warm and cold currents. Water circulation, Indian Ocean Dipole, Madden-Julian oscillation. climate change, Indian monsoon, link, and India and fisheries. These 8 dimensions are not separate topics. They are one interconnected system. The thermohaline circulation moves heat around the globe. Ocean currents redistribute that heat regionally. Water circulation links Pacific Ocean temperature to Indian atmospheric pressure. IOD modulates Arabian Sea moisture. MJO creates weekly active break cycles within the monsoon season. Climate change amplifies all of these systems, making warm SSTs warmer, making El Nino more extreme, weakening the thermohaline conveyor belt, acidifying the ocean that sustains our fisheries. And all of this ultimately determines whether India's farmers plant on time, whether reservoirs fill, whether floods devastate, whether the economy grows or shrinks. The ocean is not geography. The ocean is destiny for a nation like India. Cross promotion. This was part 2 of the ESHIKSHABYBRAJESH UPSC geography series. If you missed part 1, the Indian monsoon video, please watch it now. The link is in the description. And part 3, climate change and India's vulnerability, is coming soon. Subscribe to ESHIKSHABYBRAJESH so you do not miss it. All the best for UPSC Mains 2026. You have covered this topic completely. Now go revise the concept map and the data facts. And you are ready to write an excellent answer. This is ESHIKSHABYBRAJESH. Keep learning, keep growing.